Good day, and welcome to Optics and Refraction, Investigating Snell's Law. So this is a lab we do at my high school, and we're just going to walk you through how to use a new equation, Snell's Law, Ni sine theta I equals Nr sine theta R, the math that underlies how light bends when it moves from one substance to another. So when we actually do this, when we shine at least a red ray of light, different colors will bend at slightly different amounts. If we shine that in at 30 degrees, what you're going to see is that the light will bend and come out at approximately 22 degrees over here. So that'll be 22 degrees. In our class, we've already worked a little bit with this formula, and we've talked a little bit about indices of refraction. And so 1.33 is our number for water. But we're going to pretend we don't know that. We're going to test it experimentally. So there's a few parts to the equation. We have Ni and Nr. Ni refers to the index of refraction, or what the light is coming from in. Ni refers to your index of refraction, specifically the index of refraction for the first medium where the light is coming from. And Nr, that's the refracted index of refraction, refers to how well light slows down or bends light in the second substance, the one that the light goes into. And then we've got a couple of angles in here. Theta I, it's a fancy Greek letter that refers to angles, refers to what angle relative to the normal. And so that's been covered in a previous class as well, that this angle right in here is your angle of incidence, always measured relative to the normal. That's this theoretical line here, perpendicular to the surface. And theta R is the angle once it's moved into the new substance. Doesn't necessarily mean air and water. That's what we'll be doing in this case. And so if we're going to be doing this, Ni is coming from air, it's going into water. So in this case, your incident part of it means it's coming from air. And so the index of refraction for air is, well, if you carry enough decimal places, you run into something besides 1 even. But for the practical purposes of a high school physics lab, 1 is plenty. We're going to multiply that by sine of our angle that has come in. And on the other side, the refracted side, we're going to pretend that we don't know that the index of refraction for water is 1.33. So we're going to try to solve for that. And we found out that this came at 22 degrees inside the water. It will continue in a straight line after it hits this surface, because it hits 90 degrees. In a previous lesson, we learned that it goes straight through when hitting a square to the surface, or on the normal. Well, sine of 30, if you're going to do that in a calculator, you may not have learned how this function works in math yet, but it's simply a mathematical function similar to multiplication and division. And so you'd say sine, you put 30 into your calculator, and if you've done it right and it's in degree mode, that will be 0.5. From now on, we're not going to write the extra decimals here for the moment because it's really close to exactly 1. Nr, our index of refraction for water, and sine of 22 degrees. Sine of 22 degrees is equal to 0.37, we'll round that to 5. Our index of refraction ends up being equal to 0.5. We want to get this part over to the other side. Algebraically, we're just going to move it to the other side by doing the opposite. So multiplication is happening right here. So we divide both sides by 0.375, and that brings it to the left side. So Nr, if you take 0.5 and you divide it by 0.375, you get an answer of 1.33. We get experimentally the theoretical value for water. So that's been done well. We're going to continue on and do that again. We're going to do it for 45 degrees. And so at 45 degrees, when we did this experiment, we saw that it came out at approximately 32 degrees. And so if we're going to use the index of refraction again, so here is our formula. The index of refraction for the moment, sine theta I, if it came in at 45 degrees and it went into water, We're going to pretend we don't know that this value is 1.33. And write sine of 32 degrees on this side. Well, sine of 45 degrees is equal to 0.707. Index of refraction for water, again, that simply means how well does light slow down and bend water when light comes into it. And sine of 32 degrees is 0.53. Once we do some rounding, if we divide both sides by 0.530 here, we can make this go away. What you're left with is nr is equal to 0.707 divided by 0.53, and you get, again, an answer of about 1.33. This is one of the cool physics values that doesn't have a unit. Okay, so that only happens a little bit in physics. Okay, but one of the beautiful things about this formula is that it allows you to predict, before you even get into your equipment, what light should do. And since I wear glasses, that's part of my daily routine, I can't see well without them. An optometrist can simply take a number of values and figure out exactly how a lens should be curved to make it work. And so this is part of that, is the introduction to it. And so if the official index of refraction for water is 1.33, which we've shown experimentally, so if your angle of incidence is 20 degrees, so that would be theta I, what should the refracted angle be? So this is going to be our unknown. So if your Ni, your index of refraction from air to water, so our index of refraction for air is 1, and we're coming in at 20 degrees. Well, Nr, 1.33 is our accepted value, and sine of our angle of refraction is left unknown for the moment. Now, we do know that this, while we don't know the exact number, should be less than 20 degrees, because the light, when it goes from something that is less dense to more optically dense, like air into water, should bend towards the normal. The sine of 20 degrees is equal to 0.342. You don't have to write it here because it just will be itself. And then on our right-hand side, 1.33 times sine theta r. Similar operations to before. If we want to get this by itself, we need to get 1.33 over to the other side. And since multiplication is the operation that we're doing, we'll divide both sides by 1.33. So sine theta r will be equal to 0.342 divided by 1.33. So that's equal to about 0.257. Now here's the final trick. If you've not worked with this before, if we want to get sine and we want to move it to the other side, so this becomes by itself, the way we would write that mathematically is sine to the negative 1, or inverse sine. And to do that, this little piece right here, if you do this part, that would be your second function, and then your sine button, and then whatever you're going to try to find. Depending on your calculator, you might have to reverse this. So these are called DAL calculators, which basically means that you can punch things in as you see them. If you have a simpler calculator and you can only do one step at a time, you would write 0.257, and then you would hit the second or shift button, and then hit sine. Either way, when you do that, the second function sine of 0.257 gives you an answer of 14.9 degrees. Now, we can't ever get that accurate with our equipment, and so we see that when we did it in practice, it was in the 14 to 15 degree range, which shows us that you can actually predict before it actually happens what your light will do. That's essential for developing all sorts of different lens-based technologies, like microscopes, telescopes, glasses, and the like. Okay, so as you notice here, we're just playing to solve different aspects of the same formula. And so not only can we predict where light will go, we can predict what light should do to make something else happen. And so if we want the angle of refraction here to be 40 degrees, so that would be this part, and it's in water, so we want it to be bent at 40 degrees in water. This is our water side of the equation. This is the air side. For now, because that's what we're doing is we're going from air to water. So if we want to figure out what that angle would be, sine theta I, over here, and we're coming from air, so that's 1.00. Well, 1 times anything is itself, so that's sine theta I is equal to 1.33 times sine of 40. 1.33 times sine of 40 is equal to 0.855. If we want to get sine to the other side, that's where this comes in. Another way of saying like divided by sine. So inverse sine of 0.855. So this, before we even get there, this should be greater than 40. Because if light bends towards the normal, when it comes into a denser material, we want it to be in that material at 40 degrees, it has to be bigger than that. So inverse sine of 0.855 is equal to 58.7, so we're going to say 59 degrees. And as you can see, we're in that range when we do it as a practical experiment. You're going to be kind of in the 59 to 60 degree range. Again, noting that with our lasers being at least 2 degrees wide, we can't claim any fraction of a degree like we did up here. Okay, and so that's going to be going from light, from something that's less dense to more dense. But we can also reverse the process and send the light from the denser material to the less dense. And in this particular case, that's actually going to result in some really interesting applications and situations. It's called total internal reflection. So if you are working with a laser in real life, just be careful, make sure that it's not going into people's eyes. In our lab, we make sure that everyone arranges themselves around the outside of the classroom and make sure the lasers point to the outside, not towards windows and the like. So we're going to do the situation again, and this time we're going to shine it from the water side towards the air. So when we do that from 40 degrees down here to our drawing teacher, you're going to see that that light is going to come, and instead of going straight through, it's going to bend away from the normal and come out, kind of in the 60-ish range over here. So if that is the case, and that's what we've done, we're shining it from water into air. So the refracted angle is approximately 59 or 60 degrees. Let's do 59. If we use that information and we assume that we're coming from water into air, now, refraction means what's it going into. So now that it's going into air, air is going to be information on the right-hand side. And over here, you've got water on the left-hand side. And so if you're coming from water, and we're going to try to figure out the index of refraction for water, that means that this is our unknown right here. Now, we've already gone over in class, and we've gone over it in this tutorial. That is 1.33. So that's what we should be getting. Let's find it experimentally. Our index of refraction, an I, for water in this case. We're going to multiply that by sine of our angle of incidence. That's where the light is coming from. It's going to go into our next material, in which case it's air. The index of refraction, NR, for air is 1, and sine of our refracted angle, we'll say it's 59 degrees in this case. So to solve for this, we have to use our calculators. So sine of 40, so Ni remains our variable that we're solving for. Sine of 40 is 0.643, and sine of 59 degrees, 0.857. So now that we're solving for this, Ni is our variable we're solving for, and we want to isolate that variable. So we need to get this to the other side. We're doing multiplication. The opposite of that is division. So if we divide both sides by 0.643, Ni is going to be equal to, we get about 1.33. If it bends to 60 degrees a little bit further, then it would be a bigger index of refraction. But if it bent a little bit less, so say it was only 58 degrees, or that's what you measured, the end value would be slightly less. Okay. I think this is one of my favorites right here. So we do the same type of problem as we did before, and we try to predict what angle something is coming out at. Something really beautiful happened. And Math is a tool of physics. It's the language of physics. And so sometimes when weird things happen in math, it represents a physical reality. It can also represent that you made a mistake punching your stuff into your calculator. But here it's legit. Math fails, perhaps for the first time in your mathematical life, and it's a good thing. So if we're going to come from water, and we're going to go into air, but this time we've increased the angle, so you're all the way up to 50 degrees. What we're trying to figure out is, well, we know that it's going to have to get pretty close to the surface, because it bends away from the normal. That's straight. It's got to bend away from the normal. But how far can it go? Well, we're going to try to figure that out. Where would that rate be? So the index of refraction for water is 1.33. It's coming in here at 50 degrees. That's where our ray is. And so we try to do that, and it's going into air, and we're trying to figure out what this angle is. So that'd be like saying, what angle does the light escape at? Well, in this case, something special happens. So sine of 50 is 0.766 times 1.33. So if we take all of this and we crunch it down to 1.01-ish, 1.02 if we round, is equal to sine theta r. So people who've done a lot of math kind of get excited at this point because we know that you can't do this. So the angle of refraction is equal to inverse sine of 1.02. What you get is an error. And that's beautiful, because what it means up here is that the light can't get out. And so instead of that light going straight or bending down towards the normal, which it would normally try to do, in this case, there is no such thing. There's no index or no angle of refraction, because the light can't physically get out. It's going to totally internally reflect. Okay. There it is. You should get an error message in your calculator when you do number 7. Okay, it's going to act like a mirror. Okay, so we call that total internal reflection. If we're going to figure out at what point does the light fail to get out, everything beyond that is going to act like a mirror. So if that's the case, and we're going to try to find this place called the critical angle. So basically what we're saying is, how big does this have to be before this light up here stops getting out and acts like a mirror? So to do that, you got to figure out, when does this angle, the refracted angle, come down and touch the surface of the water, or be at 90 degrees from the normal, perpendicular to the surface. So it's trying to get into air. All right, so remember that we are going from water to air in this scenario. 1 is your index of refraction, sine theta r. Well, here's a special case, because we're trying to figure out at what point does it come right down and touch the surface. And we're coming from water, so that's 1.33 times sine of, in this case, we're going to call it our critical angle. So we'll give it a special subscript c. Again, those who are comfortable with math will know that sine of 90 is equal to 1. That makes life pretty easy over here. And so our goal is to get the critical angle by itself. Remember that sine goes with the angle, so our next step is to get the 1.33 to the other side. So sine of your critical angle is equal to 1 divided by 1.33. That's equal to 3/4, or approximately rounded. And so if you find your critical angle of this, it's going to be inverse sine of 0.75. And the answer you get is about 48.6. And when we do it in practice, it usually blinks out somewhere between about 47 to 49 degrees. It'll depend a little bit on how square you have your water dish perfectly placed. As part of the education system at my school, I get kids to do extensions of learning. So go and use what you've learned to do something cool. And in this case, what we do is we ask the kids to do an extra experiment. And so if you don't have access to, say, a nice laser light source and a semicircle of plastic, I'm not sure why you wouldn't have that kicking around at home, but in the odd case you don't have physics lab equipment at your place, kids will get a semicircle, and you can shine a laser from either side, see how much it bends, and try to find the index of the plastic. You're going to post it to me in our platform, which we call EDSB. Those who were in class, if they got done early, got to play with the other geometric shapes, things like this, and like this, and like that, and like that, and just to see what the light will do. Okay, so thank you very much. Hopefully you are a bit more comfortable with refraction and the math behind it, called Snell's law. Appreciate you taking the time to do extra learning.